A pleasant day to our dear research panelists. I am Agatha Julian Pesina from the Department of Mechanical Engineering, University of Santo Tomas, Manila, Philippines. I am one of the authors of the research entitled Development of a Practical Omnidirectional Germicidal Indoor Carrier Assistant Robot with Line Following Function, co-authored by Jordan Cheng, Russell Factor, and Brent Philip Fiadalan, with the supervision of our thesis advisor, Dr. Anthony James Bautista.
This is the outline of the study. It will give us a glimpse and an overview of the topics covered in this presentation. The first half of the presentation consists of ideas and concepts behind the study, while the second half focuses on the technical aspect of the research. So first off, the statement of the problem. The COVID-19 pandemic has been a major public health problem globally. Frontline workers or medical practitioners are more vulnerable to diseases as they were exposed to their workplaces. Furthermore, indoor spaces where people in close proximity are at high risk of acquiring the disease. In this time of crisis, indoor assistant robots play a role in providing aid to healthcare workers. Thus, the authors have a proposed solution for the aforementioned problems. A mobile robot that can navigate in indoor facilities to carry disinfecting apparatus such as UVC light. As shown in Figure 1 is the 3D CAD model of the overall design idea.
This research main objective is to develop and recommend a suitable base design of a practical omnidirectional mobile robot with the application of aiding in disinfection. Specifically, this research would like to work on the following: to design a 3D model of the robot platform and determine the factor of safety of the aluminum plate by using the SolidWorks simulation, to assemble a prototype for the robot base and customize the parameter settings according to its indoor disinfection application, to assess the assembled robot base navigation performance equipped with mechanism wheels in different testing path plans.
Once the authors deliberately assess the prototype through a series of tests and evaluations, the derived concepts and findings can be used for the implementation of an actual disinfection robot equipped with UVC lights. Germicidal indoor assistant robots will benefit commercial establishments in dire need of a thorough disinfection procedure. Thus, the helpful machine will provide a safe working environment for frontline workers. The study's acquired valuable information will benefit the researchers and students interested in pursuing and continuing similar studies. Also, it can potentially inspire and increase the interest of Filipino youth towards robotics. The study focuses on developing an indoor assistant robot that navigates a room autonomously and remotely, with a specific task of disinfection. As part of a more significant effort in developing a service robot to disinfect, the authors only focused on improving the design, automation, controls, and disinfecting feature it can offer to provide a safe working environment by maximizing the use of accessible resources. Due to limiting factors such as COVID-19 pandemic, the authors conducted experimental assessment at the comfort and safety of their homes. The authors did not include testing the effectiveness of the disinfecting properties of UVC light to various disease-causing pathogens. The robot's line follower function will only be limited to a black line and light surfaces to ensure a precise and accurate navigation. This is the graphical representation of the conceptual framework. Together with other parameters, these concepts are considered in the design and development of a mobile robot. A simple hardware, software, and control system was used as a tool for research and study. The base machine used was a four-wheel drive equipped with mechanism wheels as shown in Figure 6 and 7. 3 IR sensors were installed on the front of the robot. These sensors allow the robot to compare black lines on a white surface and vice versa, thus following a line autonomously. The robot can also be controlled manually using an integrated Bluetooth module. The rubberized external rollers attached to the whole circumference of the mecanum wheels angled at 45 degrees provides the robot the capability to move in different directions while maintaining its original position. Table 1 shows the prototype base parts and components. It consists of Arduino Mega 2560, a power source, a Bluetooth module, geared DC motors, driver motors, and IR sensors. On the other hand, Table 2 shows the prototype specifications. The overall weight of the prototype is 0.5 kilograms, max speed of 0.5 meters per second, turning radius is 0, battery capacity is at 3,400 mAh, and the maximum wireless distance transmission is capped at 10 meters. The overall system architecture of the robot prototype is shown in Figure 8. Arduino Mega 2560 serves as the main microcontroller for the comprehensive system that sends PWM commands to the geared DC motors based on sensor signals. 4 independently controlled and driven mecanum wheels were connected to separate ports of the L298N motor driver. These parts operate together to perform a specific function for the prototype to navigate the desired path. The line-following navigation model is shown in Figure 9. Mecanum wheels allow the prototype to navigate effectively in any desired direction. The robot's navigation steering capabilities can be controlled manually using an Android application connected to the HC05 Bluetooth module. The working program diagram of the base prototype following the embedded black line is shown in Figure 10. The IR sensors will first read and detect the black line of the desired path plan. If a black line comes into close proximity of the reflective surface, the microcontroller will send commands to the motor driver to maneuver accordingly with respect to the desirable track pattern.
The authors calculated the torque, UV dose, and nozzle flow rate for the theoretical calculations. The acquired calculated values were used as a reference for the parameter settings of the robot. The authors calculated the torque to select the proper motor requirements to power the robot. On the other hand, the theoretical calculations of the UV dose was calculated to determine and set an appropriate speed setting for the robot. And lastly, a theoretical computation of the spray nozzle was calculated following its fine spray disinfection application.
For the navigation performance of the prototype, the authors created various track patterns. The first path consists of 30 degrees of turns. For the second, it consists of 45 degrees of turns. And the third path consists of 90 degrees of turns. The difficulty levels were categorized as easy, medium, and hard. The authors tested the prototype robot's navigation capabilities in a pre-planned course to ensure that it can perform effectively in much more demanding tasks, as shown in Figure 13. The average total distance traveled by the robot is 5 meters. Tables 3, 4, and 5 show the data gathered from the test performed. The authors considered constant speed setting with a duty cycle of 50. The robot prototype followed embedded black lines on the floor smoothly and faster than manually controlling it. The tendency to astray from the line was shrunk from low to high. It demonstrates that the robot still requires further decoding and calibration in preparation for a much demanding path in the closed-loop test. After the initial testing, precise fine-tuning and calibration were done to the prototype. The subsequent performance assessment is done through a closed-loop test, where the prototype must overcome a much demanding path plan as shown in Figure 14. The results of the closed-loop test is shown in Table 6. The robot was successful in navigating from starting point to finish. The test only focuses on the line follower function because it executes the command with precision and accuracy. It also follows the line without any delays in comparison with a remote-controlled function. The results and analysis of the data gathered will be used to design and fabricate the actual service robot model.
The base plate simulation was considered to determine the factor of safety of the aluminum plate and review if the material can handle certain loads. As shown in Figure 15 is the factor of safety of the 3mm aluminum 1060 base plate. The simulation results show that a 3mm aluminum 1060 alloy plate has a factor of safety of 1.7, indicating that the 3mm width aluminum plate can sustain 1.7 times more load before it possibly fails. On the other hand, as shown in figure 16, is the factor of safety of the 6mm aluminum 1060 base plate. The simulation results show that a 6mm aluminum 1060 alloy plate has a factor of safety of 5.1, indicating that the 6mm width aluminum plate can sustain 5.1 times more load before it possibly fails. The value 5.1 for its factor of safety represents that a 6mm with aluminum plate is much preferable to a 3mm with aluminum plate since it can sustain a much more exerted load.
The authors successfully developed and assessed a base prototype of an omnidirectional germicidal indoor carrier assistant robot with the line-following function. An initial model was designed to visualize the general idea of the study. Base plate simulation was done to ensure that the base plate can handle external loads brought by the frame, enclosure box, and the liquid disinfectant container. The researchers built a base prototype to assess the prototype's navigation performance on various track patterns and a demanding path in the closed-loop test. In designing a course for the robot to navigate, 30 to 45 degree angle of turns must be considered to ensure a smooth and precise line tracking of the robot. The derived concepts and analysis from the prototype led the authors to several recommendations, such as the use of 30 degree and 45 degree angle of turns for path plan instead of using 90 degree angle, since turning in the angle of 90 degree had a significant possibility that the robot will deviate and astray from the path. Also, using a 6mm plate for the robot base is recommended since it can handle more weight in comparison to the 3mm plate. This is the end of our presentation, and thank you for listening.